Okay, all right. A very good evening to everyone. So let us begin today's session number 5 and we were solving the problems on the various reliability indices used for power distribution networks. And in today's session, we were going to solve problems on the reliability models that helps in analyzing the power that help in analysis of the reliability for power distribution network. And we will also solve some problems based on the various power quality issues in the power distribution networks. And this session will help you in solving the assignment number 6. So before we solve this problem, just have a quick summary about the expression and terms that will be helpful in the solving the problems. So these are some of the important terms like mean time to failure, mean time to repair, and mean time between failure. So mean time to failure, so it is denoted by m bar. So bar is representing the average term or mean that denotes the average or mean value. So that's why we take as the bar. So m bar is equal to 1 upon lambda, and where is the lambda is the mean failure rate. So mean time to failure is the operation time or uptime. This is called as the operation time or uptime for a element or system. And the second term is that mean time to repair, that we represent by R bar. So R bar is equal to 1 upon mu, where mu is the mean repair rate for a system or a element. And summation of both mean time to failure and mean time to repair, if do sum up sum both these terms, then you get the mean time between failure, MDBF, and this is denoted as T bar. And this mean time between failure is also called as the mean cycle time. And if we see this definition of mean cycle time, it is defined as the average time that it takes for the component to complete one cycle of operation, that is failure, repair, and restart. Like if you see, suppose a component begin its operation at certain time t, and then it goes on, and then it gets fault. So this time duration we call it as mean time to failure. And it has certain repairing time before it gets into operation. So like this time you can take it as mean time to repair. We take the average term because sometime it takes less time, sometimes it takes more time. So on an average we have to know that how much time a component takes to having failure, and have for the repairing how much it times required. And summation of both these mean time to failure and mean time to repair, this is called a mean cycle time. So after repairing, it again come back to operation time. It again gets connected to the system, and it again providing the services. So it is just, that's why it is called as the one cycle. So uh, re- uh, just recapitulate all these terms. And now the second important thing is that availability and unavailability of a component. So either a component is available or unavailable. So that's why it is in binary terms. So A plus mu U is equal to 1. And A is denoted as the availability of component, that is the fraction of time component is up or healthy. Availability means the component is in healthy condition and it is available to provide the service. And unavailability of component, that is fraction of time that component is down. And for finding the availability percentage and unavailability percentage, it is very simple. Like that total time duration is that, mean cycle time is that, mean time between failure MDBF, and that is the summation of mean time to repair and mean time to failure. So that is one cycle time. And if the component is unavailable, that means it bent for repairing. So you have to take at the numerator mean time to repair. So an availability percentage, how you will find it, is the ratio of mean time to repair to the mean time between failure. And just keep the terms used for mean time to repair and mean time to between failure. You will get R bar upon R bar plus M bar. And now we know that we know that R bar is mean time to repair is the reciprocal of mu, and mu is called as the mean repair rate. And this M bar, mean time to failure, that is reciprocal of lambda, and lambda is the mean failure rate. So if you are given the values of lambda and mu, you can get the unavailability percentage by using this expression, mu u is equal to lambda divided by lambda plus mu. And if you know unavailability, then you can find the availability by subtracting from 1. Our available time will be the mean time to failure, because the time duration for a component to uh, get faulty, that for that time being it is providing the services. So that's why it is the ratio of mean time to failure to the mean time between failure. And put this expression for mean time to failure and mean time between failure, you will get this one. And now if you having the constant failure rate and repair rate, failure rate is lambda and repair rate is mu. So if you having value of rate values, then you can get the availability by using this expression A equal to mu upon lambda plus mu. Till here any doubt? If there is no
No, sir.
if there is no doubt, then we can move further. These are very easy, not that much complex. Just having some new terms that you have to just take care. Now, if you are having repair components and that they are connected in series, so how you can find the mean time to failure, and how you can find the failure rate mean time to repair for the repairable components connected in series? The expression will come as this one. So for each component, they give you the failure rate, and upon summation of that failure rate, it will give sigma lambda I, and reciprocal of sigma lambda I, that will give you mean time to failure of the system for which all the components connected in series. And we know that failure rate is the reciprocal of mean time to failure, so you will get this you will get this expression. And now for finding the mean time to repair, you have to remember this expression. Like they provide the failure rate and repair rate for each component, then how you can find the average time or mean time to failure or repair for the system in which the components are connected in series. So you have to remember these two expression. If you are finding the average value or mean time for failure and repair duration, then you can find the rate values also by taking the reciprocal of them. So just remember these two expression. Now let us see the reliability of removable components connected in parallel. So mean time to failure for the components connected in parallel will be given by this expression. If the values of failure rate and repair rate is given for each component. If you know this mean time to failure, then you can find the failure rate by taking the reciprocal of it. And the second term is that mean time to repair. It is given by this expression, multiplication of repair rate upon the summation of repair rate. These two expressions are very important. So I have so only these four things you have to remember for this assignment. Other ones are very easy. Other than this, you can easily get understood if you don't remember also. But these terms I recommend just remember this term. And among these four terms, like here see M bar series, R bar series, M bar parallel, and R bar parallel. Whenever you are finding this mean time to failure for parallel components, just be careful. Be careful while applying this expression. Mean time to failure for parallel components. Why it is so? I am saying like this. You will see that if you solve the problems of assignment 6, you will get to know what is problem in this expression. Like here in the problems, whatever the things they given, they provide lambda. Lambda is the failure rate. So they provide in the terms of, yeah. So they provide in terms of faults per year. Like this failure rate is given in the terms of faults per year, while this RI, that mean time to repair, they provide you in hour. This is the mean time for repairing a certain component. So if you see this, both are having different time duration, time notation. Like this lambda is given in per year, while this R bar is given in hours. So that's causes problem. So what is the thing? You have to convert either lambda into faults per hour, or you convert R bar into in the terms of year, so that the units will get cancelled out and you will get the mean time to failure in that way. Like if first case you have assumed first case, just you remain this lambda in faults per year, and you converted, that is given R bar in hours, you converted in the years. you converted this mean time to repair in the terms of years. So you will get the answer m bar parallel, that is mean time to failure, you will get in the terms of years per fault. Right. If they asked in the terms of years per fault. Now in the second case, you can, if lambda is given in terms of faults per year, then you convert in the terms of faults per hour, and r bar just remain as it is. That is the mean repair time. So upon doing this, you will get m bar parallel in hours per fault. So take care, means just be careful while applying this expression. Other expressions having not that much problem, because in the numerator and denominator both get cancelled out with the units. But here you have to take care. You have to convert either mean, you have to convert either mean failure rate or me- um, uh, mean time to repair into the equivalent terms. We will see this. We will see some problems based on that. So till here, any doubt?
No, sir.
Okay. And certainly, if you get miss in either ways, you can, after finding this m bar parallel like in years per fault, at the end you can also convert into hours per fault by multiplying with 8716, because in 1 year, how many hours is 8760 hour. And if you approach second way, then you will get m bar parallel in hours per fault. Then certainly you can convert this into years per fault by dividing with 8760. So either way you go through, and at the end you can convert in the either unit, like m bar parallel in years per fault or m bar parallel in hours per fault. So both of you, both ways you can go through. So let us begin to solve the first problem. The first problem is that failure rate of a distribution feeder is 0 0.7 faults per 10 year. If the mean repair duration is 7 hours, determine the mean time to failure of the feeder in hour. So just start solving this problem, and after getting the answer, you type your answer in chat box. So given values are failure rate be, that is lambda. So we denote it by lambda failure rate, mean failure rate, and it is given as 0 0.7 faults per 10 year. So in each year, how many faults will be there? 0 0.07 faults. per year. So mean failure rate is given by 0.7 faults per 0.0007 faults per year, and mean repair duration, that is mean time to repair, and mean time to repair be represented by R bar. So rate is given by lambda and mu, and time duration is given by mean time duration is given by m bar and R bar. Just remember this thing. So mean repair duration is given by 7 hours. And here they have asked to find the mean time to failure. That means you have to find the m bar, and we know that m bar equal to 1 to the 1 upon lambda. So 1 upon 0.07. So so that will give you in terms of years per fault. And here if you see, they have asked to find in the hour. So multiply with 8760 upon 0.07 hours per fault. So you will get 12 1,25,142 hours per fault. So 1,25,142.86 hours per fault. So the correct answer is C. How many of you got this answer? Let me see. Rahul Patil, yes, very good. Your answer is correct. Another one also, please try. Jaswant Singh, Lekha, Priyadashini. Let us move to the next problem. Next problem is that determine the availability of the feeder described in question 1. So availability of feeder. So availability of any component that we can know that it is the ratio of mean time to failure to the mean time between failure. Sorry, that is unavailability, but uh, sorry, availability that I have to. Availability is mean time to the ratio of mean time to failure to the mean time between failure. So availability you have to that we know that it is mean time to failure is m bar, and mean time between failure is m bar plus r bar. So m bar we know that m bar we have found m bar we got 125,142.86 hours per fault, and r bar is given in the first problem. R bar is given as the 7 hours. Mean repair duration is 7 hours. So it is 7 hours. So therefore availability will be 125142.86 hours per fault, and denominator is plus this one 7, and you have to multiply with 100 so that you can get the answer in percentage, not in the terms of units. So I think it will come. So 125142.86 plus 7 and 125142.86 divided by this one, you will get 0.9994 into 100. So you will get 99.99%. Therefore D is the correct answer. How many of you got this D? Yes. Lekha, Rahul, all of you are correct. Just one, Priyadarshini. Now let us move to the next problem. Problem number 3 to problem number 5. This is common data for question 3 to question 5. Here in this problem, we have three electrical motors M1, M2, M3 running as a single unit. Among them, M1 and M2 are connected in parallel. M3 is connected in series with the parallel combination of M1 and M2. The failure rates of M1, M2, and M3 are given as 0.8 faults per year, 1.15 faults per year, zero point 0.6 faults per year, and the repair durations are 6 hours, 8 hours, and 5 hours respectively. So all the rate values are given. You have to find the duration. So we will apply those expression that we discuss here. In the first question number 3, they have asked about the mean repair duration of the parallel unit consisting of M1 and M2, and they both are connected in parallel. So mean repair duration. Mean repair duration. Mean repair duration we know we represent it by R bar. So R bar parallel, you just keep remember this expression, multiplication of all the rate values, each component rate values upon summation of all the rate values, all the repair rate values, all sorry, all the repair duration, and for multiplication of all the repair duration. So M1 and M2 are connected in parallel. So let us represent R1 bar as is given as 6 hours, and R2 bar is given as 8 hours, and R3 bar it is given as 5 hours. So you will get mean repair duration for the parallel system. Here we have to take the components M1 and M2 only. So R1 into R2 divided by R1 plus R2. R1 into R2 will be 6 into 8, 48, and R1 plus R2 14. You will get 3.42857 hours. That is 3.429 hours. So therefore B is the correct answer. Yes, Rahul Patil, just one thing. Both of you are correct. So now let us see the next problem. So in this problem, we have to find the failure rate of the parallel unit consisting of M1 and M2. So here we will use this expression for parallel unit. Mean failure rate for parallel unit, we know that this is 1 plus summation of lambda I into Ri bar plus multiplication of mean failure rate into summation of repair duration. This is the failure rate of the parallel unit. So in this expression we have to just careful. Now what we will use? We have to find in the terms of faults per year. See, faults per year. So here lambda 1, that is mean failure rate of first motor, is given as 0.848 faults per year, and lambda 2 is given as 1.15 faults per year. So these are in the faults per year values. So just remain as it is. Now we will convert the repair duration. Mean repair duration, that is R1 bar, is given as 6 hours. So we will take in the terms of year. So 6 divided by 8760. So it will give you in the terms of year. And then R2 bar is given as 8 hours. Mean repair duration is given as 8 hours. So 8 divided by 8760 years. Now we match the units. Now we will put the values in this expression. So just put all these values. So M bar parallel will be 1 plus lambda 1 is 0.8. So I will just write one more term, one more expression. So in simple form you can lambda 1 R1 plus lambda 2 R2, and denominator will be lambda 1 lambda 2 into R1 plus R2. 1 plus lambda 1 is 0.8 faults per year, and R1 is 6 divided by 8760. and lambda 2 is 1.15, R2 is 8 divided by 8760, lambda 1 is 0.8 into lambda 2 is 1.15, R1 is 6 into 6 divided by 8760 plus 8 divided by 8760. So if you see, if you just do simplification, then you will get 8760 plus 0.8 into 6 plus 1.15 into 8 divided by 0.8 into 1.15 into 6 plus 8 is 14. So if you do simplification, in the top you will get 8774 numerator, and in the denominator you will get 12.88. So you will get 681.211 in the terms of years per fault. So mean time to failure, you got 681.211 years per fault. You have to find the failure rate. So failure rate is the just reciprocal of this one. So lambda is failure rate, so it will be 1 divided by m bar. So here we have denoted as m bar parallel, so it will be 1 divided by 681.211 faults per year. So it is coming as 0.001468 faults per year. So if you match with the options, you will get A as the correct answer. Therefore, A is the correct answer. Yes, Jaswant, Priyadarshini, Rahul. Jaswant and Priyadarshini, both of you are correct. 0.00147 faults per year. Now let us see the fifth number problem. So in this problem, you have to determine the mean repair duration of the system consisting of M1. A little bit typo error. So you have to find the mean repair duration of the system consisting of M1, M2 and M3. So this is the problem. Now for the parallel system, we have already found. Now M3 is connected in series with this parallel combination. Now for series combination, what is the expression we know? Mean repair duration. So we have to find the R bar series. Did you get my point? Because we already found this for parallel combination. Now this we will use the M1 is connected in series with M2 and M3. So we will use this expression, mean repair duration for the series combination, that we know, that is summation of lambda I into Ri bar divided by summation of lambda I. So what is the final expression we can write R bar series is for parallel system we first wrote lambda parallel into R bar parallel plus lambda 3 into R3 bar divided by this lambda parallel plus lambda 3. So all these expression I think we have given, like for lambda parallel that is given by 0.001468 faults per year, and R bar parallel R bar parallel we have found in the question number 3. We have found in question number 3 that is 3.429 hours. So R bar parallel we have found as 3.429 hours, and this lambda 3 is given as lambda 3, that means mean time to failure is given as zero point 0.6 faults per year. So it is given in the express in the problem 0 0.6 faults per year, and this R3 bar is given as mean R3 bar is mean time to repair. Sorry, lambda 3 is failure rate. Failure rate is given as 0 0.6 faults per year, and R bar is mean time to repair, that is given as 5 hours. Therefore, we can find all the expression. Therefore, we can find R bar series. So just put all these values 0.001468 into 3.429 plus lambda 3 zero point 0.6 into 5 divided by 0.001468 plus zero point 0.6. So do the simplification 0. So numerator you will get 3.005 and denominator 0.001468 plus zero point 0.6. So you will get the final answer as 4.9962 hours. So correct answer is B. Any doubt in this problem or previous problem? Yes, Rahul, you are correct. Just remind me before 5 minutes that we have to switch in another meeting. We have still 30 minutes, 13 minutes. So let us go to the next problem. This is problem number 6. This is theoretical type problem. You have to tell that which of the following is a compensation type power quality improvement device used in the distribution system. First is solid state breaker, second is DVR, third is STATCOM, and D is UPFC. So which one is correct? Anyone?
Statcom.
Distribution system. Which of the following is using distribution system? A STATCOM is being used in transmission system. So STATCOM is the wrong answer. A STATCOM, a static compensator that is used in the distribution system. So it is wrong.
UPFC. Unified Power.
So it is UPFC, not UPQC. If it is UPQC, then it is correct. But it is UPFC, so it is incorrect. Unified Power Quality Conditioner. So we have two options, solid state breaker and DVR. Please unmute your mic. Yes, so DVR is being with the power quality improvement device. That means dynamic voltage
Dynamically voltage.
restorer. So these are the custom power devices that being used for power quality improvement. We have configuration type and compensation type. In the configuration type, we have we have this the network configuration devices are usually called switchgear, and they include current limiting, current breaking, and current transferring devices. So like solid state current limiter, solid state breaker, solid state transfer switch. While for in compensation type, these devices either compensate a load that is correct its power factor, unbalanced correct the power factor or unbalanced load to or improve the power quality of supplied voltage. An example for this compensation type power quality improvement custom power devices are DStatCom, distribution STATCOM, dynamic voltage restorer, and unified power quality conditioner. So here if options is given as DStatCom, then it may be it is correct, but they have provided STATCOM that is being used in the transmission system, while DStatCom is used in the distribution system. And DStatCom and DVR, these are most so dynamic voltage restorer is used for the voltage compensation, and DStatCom is used for the current compensation. DStatCom is used in the parallel, and DVR is used in the series connection. And this unified power quality conditioner is the is the combination of both DStatCom and DVR. So these things are important. So DStatCom is used for voltage compensation or current compensation. It is used for current compensation, and it is there, so it is connected in parallel, while DVR is used for voltage compensation, therefore it is connected in series. Now moving to the next problem. This is common data for question 7 to question 9. Here, if a voltage VT is applied across a single phase load and the load drives the current IT, the applied voltage and the drawn current are represented by this following expression. You have to determine the RMS voltage and RMS current. So for this type of problem, we have to take the square root of all the RMS values. So the first component is DC value. So DC value, the RMS is same as the average value. So we have to take the square of DC values, and then this is fundamental component, and the fundament RMS values of fundamental component is 230. You have to square it, and then we are given with this third harmonic component. So a square of 50, you will get the RMS values. I think it is coming as 235.58 volt. So it is just simple for finding the RMS voltage and current if it is having harmonic values and harmonic components and other DC values. So you have to take the take the a square root of summation of all the RMS square values. So you will get the equivalent RMS value. I think you all are aware of this expression. So how many of you? Piridasini, you were correct in the last problem. So just solve this problem, the new one, and then we will shift to the new meeting link. Sorry for this type of, I think I should have done this presentation in Microsoft Teams, and then we can find the RMS current again for the DC component. RMS value is 4 only. For DC component, RMS and average value both are same, and for the fundamental component, it is given as 10 volt, so it is 10 square, and then third harmonic component, it is given as 5, so 5 square. Upon doing this, you will get 11.87 ampere. Therefore, correct answer is B. So I am sharing you one link. You just connect all of these through this link. All of you through this link. 1 minute, just give me 1 second. And we will close this session and we'll continue there. Just give me 1 minute. I am ending the previous session. So all of you, I think all of you do not joined. Just one thing. Lekha, you join, please join the new session. Lekha, if you are here, please join the new session. I am ending this session. And this meeting link I have generated for like for from 8 to 9 p.m. It is same for every time. So you may save in your like anywhere, and this link is same. Means if you just miss this time, then uh, you can join from there. This meeting links from 8 to 9 p.m. just like 7 to 8 means 7 to 8 p.m. It is same for all the session. Yeah, we will solve this type problem. Don't worry, it will come. So I think we have to move faster. Assignment 6 is little bit more calculative and it require more means more time. That thing I realize. Just solve fastly so that we can cover it in 1 hour. So next is the determine the active power. So active power, how we find? We will take the each component with respect to frequency. So average values we take common, and then V1 I1 cos phi 1, and then third harmonic component V3 I3 cos phi 3. So VDC into IDC is 10 into 4, and then V1 is 230, I1 is 10 cos phi 1, cos phi 1 is 30 degree, and then V3 is 50, I3 is 5 cos. Now phi 3, how we will calculate? Phi 3 is voltage phase of voltage minus phase of current. So phase of voltage is given as 60 degree and phase of current is given as 30 degree. So it will be coming as 30 degree, and therefore cos 30. 40 plus 2300 cos 30 is 0.866, and it is 250 into 0.866. So this will give you 2248.365 watt. So B is the correct answer. How many of you got this? You just solve parallelly with me. I will move little bit faster. Find the displacement factor. And if you have any doubt, you can just interrupt me and ask if you don't understand any problem. Displacement factor, we also call it as fundamental power factor. Displacement factor, that is also called as fundamental power factor. And we take respect to fundamental component. So fundamental component is this one, both. So cos phi 1 is 30 degree. So it is 0.866 lag. Since current is lagging with respect to voltage, cos of 30 degree. So the other way you can also write displacement factor is cos phi 1 equal to P1 divided by V1 I1 if all these values are given. Now let us move to the next problem. Question number 10. Which of the following is our long duration voltage variation? Yes, cos 30 Priyadarshini, you are correct. So here in this problem, which of the following is our long duration voltage variation? Voltage sag under voltage swell over voltage. Please provide your answer in the chat box, or you can speak. Anyone? Yeah. So this I just want to note it down. So this is multiple select problem. More than one options are correct. Multiple select question. Now you tell which of following is our long duration voltage variation. So voltage sag comes under short duration. So this is incorrect. Under voltage, yes, this comes under long duration. Voltage swell also comes under short duration. Over voltage comes under long duration. So under voltage and over voltage are correct. And for short duration voltage variation, it sustains for a few cycles up to a minute, and it has been classified as voltage sag, swell, and interruption. In interruption, you can take it as momentary interruptions because it sustained for a few cycles and up to 1 minute. And for long duration voltage variation, These RMS variation in the supply voltage at the fundamental frequency for periods more than 1 minute, like over voltage, under voltage, and sustained interruption that sustains for longer time. So now moving to the next problem. Here, this is common data for question 11 to question 13, and this uh, and in this problem you have a radial distribution feeder having three sections 3 km per length. Each feeder section suffers for two faults per kilometer in 10 years, and the average repair duration for each feeder section is 1.5 hour. Determine the average repair duration of the feeder. So just find out. I am just coming in 2 minutes. Sorry guys. So here mean failure rate, we know that it is denoted by lambda. So lambda 1, lambda 2, and lambda 3 all are equal for each feeder section, and it is given at 2 faults per kilometer in 3 years, and each feeder section is of 3 kilometer. So 2 into 3, that is, and divided by 10. So you will get 0.6 faults per year. And now mean repair duration is also given as 1.5 hour. So R1 bar, R2 bar, R3 bar all are equal. So it is given as 1.5 hour. And we know that for series connection, how we can find mean repair duration, mean time to repair. This is given as summation of lambda I Ri bar divided by summation of lambda I. Just elaborate this: lambda 1 R1 bar plus lambda 2 R2 bar plus lambda 3 R3 bar divided by lambda 1 plus lambda 2 plus lambda 3. So if you see, so put all these values 0.6 into 1.5, so all are equal, so it will get multiplied with 3, and lambda 1 plus lambda 2 plus lambda 3, it is 0.6 into 3, so you will get 1.5 hours. So correct answer is B. How many of you got this answer? Yes, Rahul Patil, you are correct. Rahul Patil, just one. Priyadarshini, you are correct. Now move to the next problem. Determine the failure rate of the feeder. Failure rate means lambda series you have to find. We know that failure rate of the series connection is sigma lambda I. So it is lambda 1 plus lambda 2 plus lambda 3. So it will give you 1.8. 8 faults per year, because for each section it is 0.6 faults per year. Therefore, C is the correct answer. 1.8 faults per year. Yes, Rahul Patil, very good. Next problem, determine the availability of the feeder. So, availability of the feeder, how you can find? We know that availability is mean time to failure. It is ratio of mean time to the failure, the mean time between failure, and it is denoted as m bar. So here we have take it as series connection. So m bar series plus m bar series plus r bar series, that average repair duration plus average fault duration, average failure duration. So m bar series, how we can find? We have found the failure rate. So from there we can get the mean failure duration. So 1 divided by lambda series, 1 divided by lambda series is 1 divided by 1.8 years per fault. 8 years per fault. Now R bar series, how we can find? R bar series we have found. R bar series is given as 1.5 hours. R bar series is given as 1.5 hours. So M bar series is given in terms of years, while R bar series is given at 1.5 hours per fault. So therefore, we have to convert in the same unit. It is not fault. So repair, it is average repair duration. So you have to convert into the hours duration. So it is 8760 divided by 1.8 hours per fault. Just put all this in, you will get the availability percentage. M bar series is 8760 divided by 1.8 divided by 8760 divided by 1.8 plus 1.5 into multiplied 100% to get in percentage. So we will get approximately 99.9692%. Therefore, therefore D is the correct answer. 99.97%. How many of you got this? Yes, Rahul Patil, correct. Now let us move to the next problem. If a unit is having failure rate of 0.6 faults per year, determine its mean time to failure in hour. So failure rate is given as lambda. So it is given as 0.6 faults per hour per year. And we know that mean time to failure is the reciprocal of rate values. And failure rate is given as 1 lambda 0.6 faults per year. So it is 1 divided by 0.6 years per fault. Now we have to find this value in hour. So you have to multiply with 8760 divided by 0.6 hours per fault. So you will get 14,600 hours per fault. Therefore, B is the correct answer. Yes, Jaswant, Rahul, Priyadarshini, all of you are doing good. And moving to the next part, problem 15 to 17. Uh, there are two electrical motors operating in parallel to form a unit. The failure rates, if this, yes, they are connected in parallel. The failure rate of the motors are zero point 0.8 faults per year, 1.2 faults to 5 faults per year, and the repair duration are 6 and 8 hours respectively. You have to find the average repair duration of the unit. So what are the things we have given? We are we are given with lambda 1 zero point 0.8 faults per year, that is failure rate of first motor, and lambda 2 that is given as 1.25 faults per year, and then this R1 bar is given mean time to repair, that is 6 hours, and then for second motor R2 bar is given as 8 hours. And we know that for parallel units, if you are finding the mean repair time, then it is the multiplication of each mean repair duration upon summation of each repair duration. This we know. Just apply this, that will become R1 bar into R2 bar divided by R1 bar plus R2 bar. So you will get 6 into 8, and 6 plus 8 is 14. So 48 we have for 3.43 hours. 3.43 hours. This is the answer. Therefore, B is the correct answer. Yes, 3.43. Just want all of you are correct, Pidasani. Now move to the next problem. Here we have to find the availability of the unit. So again we will use the same expression. But for finding the availability, we have to find the mean time to failure because we don't know this. So first we will find the mean time to failure of the parallel unit. So we know that m bar parallel is given as 1 plus summation lambda I ri, and multiplication of lambda into summation of ri. In other terms, it is 1 plus lambda I lambda 1 r1 bar plus lambda 2 r2 bar divided by lambda 1 into lambda 2 r1 bar plus r2 bar. And I already told you, just be careful while applying this expression. So here lambda 1 is given in faults per year while r1 is given in hours. So we will convert lambda 1 in terms of hours, so that all the terms we get in hour values. So lambda 1 is given as failure rate is 0.8 faults per year. So if we convert into hour, then it will be 0.8 divided by 8760, and R1 value we know that it is 6, and then lambda 2 is 1.25 faults per year. So it will be divided by 8760 to get in hours, and multiplied with 8, that is R2 bar value, and then 0.8 divided by 8760 into 0.1.25 divided by 8760 into R1 plus R2, 6 plus 8. So you will get 7.67 into 10 to the power 7. divided by 14. So we will get 5481258 plus 2 hours per fault that we found m bar parallel, and we already found r bar parallel, that is coming as 3.43 hours. 3.43 hours. Now we know that availability is mean time to failure by total cycle time, that is r bar plus m bar. M bar is given as 5548125.2 divided by 54812.2 plus r bar is 3.43. So you will get very large value, and sorry, you have to multiply with 100 to get in percentage form. So you will get 99.999. If you go further, then it is coming at 3742%. It is approximately equal to 99.999%. Therefore, A is the correct answer. Yes, I think no one tried this. So let us move to the next problem. Here you have to find the failure rate of the unit. Failure rate of the unit means mean failure rate. So lambda parallel, you have to find that is the reciprocal of mean time to failure. So m bar parallel we have already found. So 1 divided by 5481258.2, that is hours per fault. So reciprocal of it will give you faults per hour. Faults per hour. So here they are asking in faults per year. So multiply with 8760 and then 5481258.2 faults per year. So it will give you 0.001598.2. So approximately equal to 0.0016 faults per year. So B is the correct answer. I think no one is trying. Yes, Priyadarshini, you are correct. And now moving to the next problem, problem 18. Which of the following is not a short duration power quality problem? Just we have covered. Just tell me fast. Which of the following is not a,
Over voltage.
yeah, over voltage. Very good. Voltage high, voltage fuel, voltage flicker, all are long duration, all are short duration voltage variation. Here it is asking about not a short duration. So over voltage is a long duration voltage variation. So I have just take note down this thing. Now moving to the next problem. Which of the following components will be present in balance 3 base voltage? Positive sequence voltage, negative sequence voltage, zero sequence voltage, all of these. Anyone? Which of the following components will be present in balance 3 phase voltage? Any idea? Rahul, Jaswant, Priyadarshini, Lekha. Any idea about this problem? Just tell something so that I can understood what is your running your mind. So as it is simple balance three pose voltage, so only positive sequence voltage will present. The negative sequence and zero sequence voltage all are zero in voltage. While in unbalanced three phase system, all components are present. From the Fortescue theorem, it is the basic of power system. You can go through it. So uh, in unbalanced system, all you can convert a unbalanced system into three sequence network, that is positive sequence component, negative sequence component, zero sequence components, and these sequence components are balanced in itself. Means like you can convert a unbalanced system into a balanced system with these three sequence components. So that is the fundamental. While if a system is already balanced, that means only positive sequence components will present there. Now the next problem, difference between facts and custom power devices is, and this problem is multiple select problem. Multiple choices are correct. Multiple select question. So first option is facts devices are using power transmission networks and custom power devices in power distribution networks. And the second is facts and distribution just reciprocal of first. And C option is fact devices construction and control to work in an unbalanced system, while custom power devices are constructed and controlled to work in a balanced system. One thing just we want to revise that we know that transmission systems are usually of balanced in nature, while distribution systems are usually of unbalanced in nature. So now tell me which of the following should be correct. So we know that facts flexible AC transmission system that we used in the power transmission networks, and custom power devices we used in the power distribution network. So A is the correct. And while we B the reciprocal, so it is incorrect. And C option is fax device are constructed and controlled in an unbalanced system. Unbalanced system means distribution, distribution system, distribution system. So we know that fax devices are in transmission system. So it is incorrect. While last option is fax devices are constructed and controlled to work in balanced system, that is transmission system, and custom power devices are constructed and controlled to work in unbalanced system, that is distribution system. Therefore, D is the correct option. Now moving to the last part of one of the more important part of this today's lecture, today's session, that is reliability for the parallel series combination. That if you are given a block diagram, how you can find the reliability of that block diagram. So like for the series combination, and each component has the identical reliability that is denoted by R, then the R equivalent will just multiply all this. So for the series connection, you have to just multiply all the reliability components. So you will get R to the power n. So R equivalent for series system is, you can write in this also, R series is, you have to take the multiplication of all this reliability of all the reliability value for each component, and just multiply. Here all components have identical reliability value, so it is R to the power n. Now for this parallel system, you have to subtract from 1 minus whatever the common, like for first system the reliability value is R, for second system reliability value is R, for third component reliability value is R. So 1 minus R, and it goes on 1 minus R, so it is continuing. and take it as m, not n. So like if there are m components that are connected parallelly in a system, then R equivalent will be like this. So you can say R parallel value equivalent will be 1 minus R to the power m. So just have a you have just keep in mind these two expression R series and R parallel. In a series you have to just multiply all the reliability values, and in parallel you have to subtract from 1 and then 1 minus each reliability values for each component. Like this you can find this equivalent reliability for this for a block diagram that are connected in series or parallel. So let us take one example based on this concept. So here you have to find the equivalent reliability of each system configuration in favor, assuming that each component has indicated reliability. Like first is the series connection, and then in the B we have series and parallel combination, and in C we have parallel combination, and in D parallel and series configuration. You have to find the reliability. So I am going to find for first one. Like let us take it as R1, R2. R1 is given as 0.9, R2 is given as 0.99, R3 is given as 0.95. So for first, we know that you have to just multiply all the reliability values. So it is R1 into R2 into R3, R1 into R2 into R3, 0.90 into 0.99 into 0.95. So you will get 0.84 0.84645. So this is the answer for the first equivalent reliability for this first A number system. So we got the solution for the A part. Now for B part. For B part we got a step by step, like we first found this one. So let us take it as R equivalent 1 for this series connection, and let us take it as R equivalent 2 for this series connection. So for B part R equivalent 1, and here we denote it as R1. R1 is given as 0.90, R2 is given as 0.90, and R3 is given as 0.98, and R4 is given as 0.98. So R equivalent 1 will be 0.90 into 0.90. So you will get 0.81. Now for R equivalent 2, you will get 0.98 into 0.98 because this is series combination. So you will get 0.9604. Now it becomes like this. So one, this one. So it is parallel combination. So this has reliability of 0.81 and this has reliability of 0.9604. So so then we have the we have to find the reliability of this parallel system. How we will find? We know that you have to subtract from 1, then 1 minus, and again you have to put in bracket 1 minus this reliability of first component 0.81, and then 1 minus 0.9604. So you will get 0.992476. So this is the answer for the B block diagram. Now let us solve for C. C is very easy. So in C all the systems are connected in parallel. So can anyone tell, like for C part, what should be the R equivalent? Can anyone tell? This is simple. I think you are not getting it if you are not able to answer. Rahul, you are giving the correct answer. I'm asking about C part. How you will get, what is the expression for C? R equivalent. Priyadarshini, Jaswant, Lekha. I think I don't know you are here or not. So let me just write. So for parallel combination, how you are going to write 1 minus, like suppose here we denote it as R1 and we denote it as R2 and we denote it as R3. So 1 minus R1 into 1 minus R2 into 1 minus R3. So it will be 1 minus 1 minus 0.6, 1 minus 0.99 it is given, and then R3 is given as 1.07. So it is 1 minus 0.4 into 0.01 into 0.3. So it will give you 0.9988 as the answer. Now the last part D. So in the last part, this first parallel combination. So first we are finding this R equivalent of this one. So let us take it as R equivalent 1, and for this one let us take it as R equivalent 2. So for the parallel combination we know that R equivalent 1 will be 1 minus 1 minus 0.90, 1 minus 0.98. So it will be 1 minus 0.1 into 0.02. So it will giving us 1 minus 0.002, 0.998, and R equivalent 2 will be, I think both are identical. So 0.90, 0.92, so R equivalent 2 is also coming as 0.998, 0.998. Hence, the final R equivalent will be, it is series connection, so you have to just multiply both the values 0.998. You will get the final answer 0.996004, that is approximately equal 0.996. This is the answer. Priyadarshini, are you able to solve the problem 2 of assignment 6 from now? You were asking problem that how I will solve this assignment 6 question number 2. Now you got it? Yes, okay. Now we are moving to the last problem of today's session. I don't know how many times I have left. We have 20 minutes. Okay, all right. So this is the problem, and this type of problem is given in your assignment 6. So find out the load voltage and its THD percentage. So here there are two components in current, and and this source is represented by Thevenin equivalent of voltage 230 plus J0 volt with respect to the fundamental component. So these values are given with respect to fundamental component, that is with respect to fundamental frequency omega. So this is given means at the load terminal source is represented by Thevenin equivalent of voltage 230 plus J0 volt and impedance of 1 plus J1 ohm. This is corresponding to frequency omega. If it is not given also, you have to consider with respect to the fundamental frequency. Now you have to find out the load voltage in the terms of instantaneous so that you can get the RMS load voltage. So how we will find it? So here since two components are there, two components of current are there, so we go by superposition theorem with respect to each frequency component, and at the end we will just sum up the voltage. So here we are going to apply this superposition theorem. Applying superposition theorem. This current expression drawn by load is given as IT. So you can represent IT as two parts, I1T plus I3T. So we are going to considering for first part for I1T. For I1T, it is given as 20 root 2 sine omega t minus 30 degree. It is the instantaneous form. So we can write it in the terms of phasor value. In phasor value, this is I1 bar equal to 20 at the angle of minus 30 degree ampere. And let us take it as J1 with respect to fundamental frequency. So J1 is 1 plus J1 ohm. So you will get root 2 at the angle of 45 degree. This in terms of ohm. Now making the circuit, this is I1T and source is 230 at the angle of 0 volt, and this is 1 plus J1 ohm. So you can write it at root 2 at the angle of 45 degree ohm. And this is here a voltage is connected, so we have to find here a load is connected, we have to find the voltage across the load. So take it as VL1. So VL1 will come as 230 minus I1 var Z1. So it is 230 minus 20 at the angle of minus 30 degree. 1 plus J1 ohm is root 2 at the angle of 45 degree. So if you do, then you will get in Cartesian form 202.68 minus J7.32, and in phasor form you will get 202.812 minus 2.068 degree volt. So just be careful, we are taking in the phasor form we are taking the RMS value. So this value we got the RMS one, 202.810, that is voltage across load. If we are considering the fundamental component, fundamental frequency component, then we get this one voltage. This one is the RMS voltage. Now we will apply for I3T. Now for the third harmonic component. Now for third harmonic component of current is 10 root 2 sine 3 omega t minus 60 degree ohm. So in phasor form, you will get I3 bar as 10 at the angle of minus 60 degree ampere. And Z3, how much you got? Can anyone tell? If Z1 we have wrote 1 plus J1, how much voltage we will get in Z3? Any idea? Rahul, Priyadarshini, Jaswant, Lekha?
It may remains constant.
No, no. How it will constant? Because if it is resistive component, then it remains constant. But it is not the resistive component only. 1 plus J3 ohm. How it is coming? Because we know that R plus Jx and X we know that omega L. So 2 pi FL. So F is going to change 3 times F. So this becomes 3 times. So 1 plus J3 ohm. And resistive component will remain as same as it is. But the reactive component, it got changed. 71.565 ohm. Now, if we make this equivalent circuit, then source will be not there for this third harmonic component of current, because it is with respect to source voltage, it with respect to fundamental one 230 plus J0, but it is not with respect to third harmonic. So only this impedance will in this third harmonic component of current. So it is 3.16 at the angle of 71.565 ohm. And this is the voltage. Sorry, this is the voltage we got across the load. So it is VL3. And since current direction is this side, like I3 bar is, so VL3 will be, it is minus, because if we take polarity this side plus minus, then it will be minus. So VL3 will be minus of I3 bar into Z3. So minus of I3 is 10 at the angle of minus 60 degree, and Z3 will be 3.16 at the angle of 71.565 ohm. So you will get minus, just take just outside. So you will get 30.98 plus J 6.34 volt, and in phasor form minus 31.623 at the angle of 11.565 degree volt. And if you want to, if you take minus inside, then minus will represent minus 180 degrees, so it will come as 3.623 at the angle of minus 168.43 degree volt. So final expression will be, now we got both the components of voltage across the load. So therefore we can write VLT. So VLT, this is the RMS value 202.81. So you have to multiply with root 2. So it will coming as 200 286.82 sine omega t minus 0.068 degree, and VL3 will be, this is minus, so minus 44.72 sine of 3 omega t plus 11.565 degree. This is the instantaneous expression. So we have written VLT in terms of both. VLT is the summation of fundamental one, that is VL1T plus third harmonic component VL3T. So that is the expression for the voltage across the load. Now they may ask you to find the voltage across the load RMS. So RMS voltage across the load, VL RMS. You know that you have to take the under root of RMS square. So for the first component, RMS value is 202.812, a square of it, and for the third harmonic component, you have to a square of 31.623 degree, 623 a square. What value we are getting? Can anyone tell? 202.812 square plus 31.623 square, 6123 square. So you will get 42132.72, and taking under root of it, it will give you 205.26 volt. So this is the RMS voltage across the load we got. Now in the second part, they have asked you to find the percentage THD in the load voltage. So we know that THD is the percentage THD. What is the expression of this? Is the ratio of harmonic component to the fundamental component. We know it. So THD is the summation of n to infinity, that is harmonic voltage values Vn square divided by V1. So RMS of harmonic voltage to the fundamental voltage, and it get multiplied with 100 to get the answer in percentage. Since here only one harmonic component there, V3, third harmonic component, so top will be V3 and the denominator will be V1, and this V3 voltage, how much we got? 31.623. Here we can see 31.623, and the fundamental we got 202.812 into 100. So you will get 0.1559 into 100. So it is coming as 15.6% THD in the load voltage with the answer. RMS load voltage will be 205.26 volt, and the THD load voltage percentage THD in the load voltage is 15.6%. Any doubt till here? Okay, we are able to finish in time. Jaswant, Pridasni, Rahul, Lekha. Any doubt? I think
Sir, I have one doubt.
yes,
Sir, how you take the expression v of t 286.82 sine omega t minus
yes.
this?
So
Ah, yes, yes.
this one is okay. 1 minute. So phasor value we always write in the RMS term, while this instantaneous term we write in the maximum value. So if you write in the phasor, so if you write in the terms of RMS value also, then you will write in like this: 202 into 812 root 2 sine omega t minus 2.068 degree, and this one will be the VL3, the minus 33.623 into root 2 sine 3 omega t plus 11.563. This is the instantaneous value, and just multiplication with root 2 you will get the this value. We already wrote 286.82, so you will get this value: 286.82 sine omega 2 minus 2.086 degree minus 44.72 sine 3 omega t plus 11.563 degree volt. Minus you can take in the terms of this one also. If you take minus, then add subtract minus 180 degree from 11.563 degree. So you will get another term also with respect to angle, but the RMS load voltage will not change. This will change only the phase angle. So RMS voltage will not change. So whatever the RMS voltage we got, VL RMS, that will 205.26 volt. It remains unchanged. Either you write this in uh, like you may write in this form also. I may write this one also. Like 286.82 sine omega t minus 2.086 degree minus plus, so take minus inside, plus 44 point sine 3 omega t minus 168.43 degree volt. So this may you can write. So okay, this is, I hope you will be able to solve the problems of assignment 6. We will meet in the next session. Thank you for attending the session. Goodbye.